Hello and welcome to my first session. So our subject here is strength of materials. So let me discuss first what will be expected on what are the topics to be discussed for the whole duration of our session. So as we can see, for the course outline, we have 6 weeks for this mid-year. So for the week 1, we are going to have the introduction, strength of materials compared to engineering mechanics, the types of forces, stresses, what are the units of measurements, type of stresses, or these are actually analysis of internal reaction of external forces like simple stresses, normal stresses, shear stress, bearing stress. And then we will proceed to the effects of these stresses through the simple strain, conditions where the strain is constant, relationship between the stress and strain, stages in deformation and strain in a material. So for the second week, we will discuss working stress, allowable stresses, factor of safety, the modulus of resilience, modulus of toughness, ultimate strength, rupture strength, shearing deformation, Poisson's ratio, biaxial deformation, triaxial deformation. So all of this refers to the chapter which discusses the simple strain. On the week 3, this is just an extension of the other topics from chapter 2. We have the bulk modulus of elasticity, modulus of volume expansion, indeterminate members, thermal stresses, torsional stress, the angle of twist, power transmitted by the shaft, helical spring, spring in series and parallel, shear and moment diagrams, types of loading, shear diagram, moment diagram, methods of establishing the diagrams, and then we will learn how to write the shear and moment equations, relationship between load, shear, and moment, and then we proceed to the beam stresses, discussing the flexure formula, section modulus, economic sections, horizontal shearing stress, shear flow. So these are the most important topics in strength of materials we wanted to know that is essential in your design subjects later on, like reinforced concrete, steel and timber design, and other design, structural design that we need to know. Okay, so for the introduction, may I flash to you a series of slides as an introduction for our subject. So, of course, the title of this subject is Mechanics of Materials. So this is actually the old title, Strength of Materials. Okay, so let us first understand what is the difference between your mechanics and strength of materials. By the way, your mechanics is actually the statics and the dynamics that is a prerequisite for this subject. So, for your engineering mechanics, it deals with the effects of external forces to a rigid body. We presume or we assume that the body is unyielding, material does not fail. So, if we could recall the concepts in engineering mechanics, we are more on determining the forces or the force reactions, whether this force is accelerating the body or not. But in engineering mechanics, we wanted that we have to satisfy the axioms of mechanics wherein the the body should be always in equilibrium. So we apply the three equilibrium equations like summation forces vertical, summation forces horizontal, and the rotation, summation moments, so for the force times distance in a certain point. So our concern is more on the force only, but we do not investigate what are the effects of these external forces to a rigid body, because as we all know, there's no such thing as unyielding body or unyielding material. So, but we extend our knowledge in strength of materials so that we will have an investigation of these external forces on what will be its internal effects on the body. Say for example, if the body is subjected to a certain force, does this material will break, will bend, will elongate, will contract? Would it break, or would it resist sufficiently the external forces? Somehow this material would also fail if it will reach the allowable stresses that this material is subjected. Okay, so in this subject, in strength of materials, bodies no longer assumed to be rigid and materials are subjected to deformation. So there's no such thing as material not yielding, okay? So all of material will fail or will deform. Only that in engineering, we need to control this deformation so that we will be having a tolerable one that is essential to a safe and resilient building structure or any structure related to engineering. So deformation is actually of our main interest here, as well as the strength and rigidity. So in order to have a visual interpretation on the comparison between the two subject matter, let us consider here a setup wherein we will use a fulcrum bar to lift this weight. Okay, so why do we need to use a fulcrum bar? Because fulcrum bar is a type of a tool or equipment to make or to reduce the force we need in order to lift this weight. Okay, so in mechanics, our point of interest is that how much P to be applied in order to lift this weight. Okay, so basically we can compute that by taking moments at F and equating it to 0. Why 0? Because 0 is an equilibrium condition, right? It is a balance condition. So once we exceeded 0, it will begin to impede motion. So that's it. So what is the P needed? Okay, so that is the mechanics, our concern in mechanics. In strength of materials, we are going to investigate whether this crowbar is it sufficient enough to lift the weight without breaking, or this fulcrum bar will be subjected to a certain bending. Baka mamaya magbend, or it will have a buckling effect on this because the weight is too much. Okay, so that is our concern, the deformation. Or would this fulcrum bar will break? Okay, so that is our main concern in strength of materials. So in short, the internal effects would have an implication on the strength of the material will be used. It may be that this material is a steel. We have a property for steel or the strength properties of steel, or if this fulcrum bar is a timber, of course we have a different strength or strength properties for that material. So in there are a variety of strength properties in different material. So remember that. So hindi pare-parehas ang properties in terms of strength. Okay. So in strength of materials, we need to have an exploratory section wherein we need to cut the material and then investigate the effects of the external forces. Say we have F1, F2, F3, a series of forces, and then what are the effects of these external forces in this exploratory section of the certain member. Okay, so let us have here an example. Say we have here a parallel pip with different axes. Say we have here the X, Y axis and the Z axis. I'll just have here a scenario of different forces to be applied on those axes. If we are going to consider here the axis on X, if we are going to apply a force parallel to the member, that is what we call the normal force. So the normal force will have a normal stress also, a corresponding normal stress. What is normal stress all about? So normal stress, kung parallel yan, it could either elongate or it could compress the structural member. So that is the effect. So we term that, if we elongate, we term that as a tensile force, and if it is compressing or shortening the material, that is what we call compressive force. Okay, so that's it. So, and if we have to apply here, this is what we call a couple force. A couple force on this parallel axis X. What will be the effect on that? So it will twist the material, and that is what we call torsional force. Okay, it will twist the material, that is torsion, or there will be a corresponding torsional stress if we apply a couple in an axis that is parallel to the member. Okay, so that is for the x-axis. X-axis here is parallel to the member. Okay, next, if we consider another axis, say y-axis. So this is the y-axis. This is the y-axis. And if we apply a force parallel to the y-axis, and we know that the y-axis is perpendicular to the structural member, the effect here is shearing stress. Shearing stress. So what is shearing stress? A shearing stress is a cutting force. Okay? So just imagine a knife. For example, you are going to cut a bread. If we have a knife, the cutting force is actually perpendicular to that. But that is not always the case. It could be that the knife could be diagonal. Okay? So in whatever direction, whatever this knife passes through, that is what we call shear force. So it could pass through a perpendicular slice or a diagonal slice. So that is what we call the shear force. Okay. Now, if on the y-axis we will apply here a couple again, what will be the effect on that body? So the effect is it will have a bending. So imagine we apply this to this axis, and the effect is the bending along the x-axis, or in short, In x-axis, it could bend leftwards or outwards, inwards or outwards. So in this case, we will be having an outwards bending on that structural member. So that is the effect of that forces. A couple and force on the y-axis will have a shear and a bending. And then going to the z-axis, sa z-axis, it will have the same effect as the y-axis, only that different direction. So if we are going to apply here a force Z on the Z-axis, of course it will shear, it will cut that sideways. It will cut the member sideways. And if we have to apply a couple there, it will bend the structural member again along the x-axis, but it is now vertical. It is either this member shall concave upwards or it shall concave downwards. So a while ago, this bending force or this couple would tend to bend this sideways. But if we have a z-axis or a couple in the z-axis, it will bend it upwards or downwards. Just the same, that is bending. Okay? So the same effect on the y-axis and the z-axis. The x-axis, on the x-axis we have a twisting and a normal stress, or it could either be tension or compression. So those are bending moments. We have axial loads or normal loads or axial loads. Axial and normal is just the same term, tension or compression. Okay, so for the force, we have the shear or tangential force. Shear force, tangential force is denoted by capital letter V. Okay, and then we have the twisting on that. Okay, so this is just the same concept, only that we have 2D presentation here. This is an exploratory section for the X and Y direction. So as we can see, if it is parallel to the member, so this is the member, parallel force, we have the axial force, and then we have here the bending moment. It will bend that downwards, of course. And then this one is a shear force. Again, shear force is not always perpendicular. It could be diagonal. So if it is diagonal, the shear force is diagonal. We will just get the component of the parallel force. Okay, or the tangential force, what we call tangential force. So basically, we need to recall our knowledge in force components. Okay, so 3D, in the 3D, just the same, we will have the bending moment, shear force, torsional moment, axial force, shear force, bending moment along Z or MZ. So that's it. So for those forces, there are corresponding stresses. We have tensional stress here, and then we have the compressional stress. So as we all know, the tensional stress would tend to elongate the member, and then compressional stress would tend to shorten the member, and the shear stress would tend to cut the member or to slice the member. So the thing here is to slice the member for the shear stress. Okay, so the simple stress is a condition where stress is constant or uniformly distributed. So simple stress or normal stress could either be compressive or tensile stress. So simple stresses are axial stress, Axial stress could be tensile or compressive stress. And then another example of simple stress is the shear stress, and the other one is the bearing stress. So the general formula is denoted by sigma is equal to the force all over the area. Force all over the area. As for our unit, we will stick to the English unit. We have megapascals. So megapascal, it could be meganewton per square meter, or it could be newton per millimeter squared. So what is important in using this simple formula, kaya nga tinawag na simple, do not make it complicated because this is simple, just simple P all over A. And then the unit, just using this formula, simple formula, just use a consistent unit. When we have a P, you should express this in meganewton. When we use meganewton, we pair it with square meter. Or if we have to use Newton, we should pair it with millimeter squared. Okay? So that's it. So let me flash here a short or a video clip I have downloaded for you to have a review and brief on that on those concepts. Okay?